the night sky over Saransk, Mordovia on November 10, 2025. At 2-3 hours, a swarm of tiny lights raced toward what was supposed to be a safe factory. Not B-52 bombers, not a squadron of heavy fighters, but 48 drones, a hybrid creation of civilian engineering and battlefield artificial intelligence. When the Krasuka 4 electronic warfare system unleashed waves of jamming energy across every GPS frequency, the decisive moment came. The machines did not retreat. They switched to seeing with their own eyes and pressed on. This was no longer a contest of big versus bigger, but an equation, software and numbers, defeating the expensive and the rare. The question before us is simple yet chilling when $1 million defense is forced to spend its own ammunition. Who is truly losing the war? Do not look away, because what happens next? 4 real drones will rewrite the map of the Russian rear lines. The rear areas are no longer a safe place. The Saransk factory in Mordovia on the 10th of November 2025 was the heart that produced hundreds of thousands of mines, a tactical reserve the defenders treated as insurance for every front. Russia built a layered air defense network. The S-400 handled long range, Pantsir, S-1 protected short range, and Krasuka 4 stood behind an electronic curtain to blind the enemy's navigation. On paper, it was a complete defensive ring. In the field, it was an economic problem. Cost is what decides the game. A single interceptor can be worth hundreds of thousands of dollars to millions of dollars. A battlefield drone, cheap by comparison, may cost only a few thousand to a few tens of thousands of dollars. When one side can force the opponent to expend expensive ammunition on a cheap target, the balance flips instantly. At Saransk, the scenario played out as a chain of calculations. Krasuka 4 dumped GPS jamming energy, forcing the unmanned aerial vehicles to change modes. 44 decoys appeared on the radar like a swarm, prompting the Pantsir S-1 to fire salvos of missiles and bleed its stocks. Meanwhile, 4 real AQ, 400 seconds, equipped with image-based artificial intelligence, quietly tracked the target. This was not merely an attack. It was a cost equation applied to warfare, where software, data, and numbers can shatter a defense built from quality and money. But what software and tactics did Ukraine use to overcome electronic warfare, and how cheap were they? At the heart of the Saransk strike was not a single legendary missile or an iconic gun, but a reverse-engineered design philosophy, cheap, clever, and scalable by numbers. The main characters here were a class of UAVs and loitering munitions built on a cheap-first, software-first, modular philosophy, lightweight airframes made from common materials, commercial sensors, and a lean layer of software that can be updated and optimized for low-cost combat. Each AQ-400 or Scythe in the formation is not meant to be a standalone technical marvel, but a node in a combat network. Losing a few does not collapse the plan, because the real power lies in swarm tactics, in data, and in rapid adaptability. When the Krasuka 4 unloaded GPS jamming, the primary weakness of many UAV platforms was exposed, but that was also the moment the software-first idea proved its worth. Instead of stopping when satellite signals were lost, systems designed this way switched to a vision mode. They used downward-facing cameras to match live images against preloaded satellite maps, relying on fixed terrain features, roads and structures to interpolate relative position. At its core, this is not some mystical trick, but a shift in power. Software and data enable inexpensive platforms to operate inside an electronic warfare environment, turning electronic warfare from an absolute defensive advantage into a surmountable challenge. The method has limits. It depends on the quality of the background imagery, illumination, and weather, but in an attack carefully prepared with ISR and SIGINT, it becomes a life or death switch. At the same time, the decoy swarm tactic converts quantity into strategic strike power. 44 decoy drones, simple in build but sufficiently convincing on radar, appear in unison and force the Pantsir S-1 to expend expensive missiles on cheap frames. This is a cold, straightforward economic calculation. make the enemy's air defenses spend hundreds of thousands to millions of dollars on targets worth only a few $1,000s. When the system fires 2 volleys and must reload, a momentary gap appears, and that gap is the opening for the few real UAVs to reach the target. Not by the superior power of each drone, but by cost, calculus, and timing that is the essence of low-cost warfare. Equally crucial is the masking capability, grounded in an understanding of enemy logistics, habits, and electronic signatures. Ukrainian intelligence tracked resupply schedules, radio call signs, and recurring indicators to know exactly when a supply truck would appear. 4-strike UAVs, fitted with warheads, exploited the truck's thermal and radar signature to hide not by sheltering behind a building or in tree cover, but by blending into everyday activity considered harmless. From an analytical viewpoint, this is a clear example of how SIGINT and HUMINT coordinate with software and battlefield drones to maximize surprise without raising the physical cost of the platforms. Platform variants coexisted to serve different strategic aims. A depot, attack model with a relatively small but precise warhead to disrupt production lines or stockpiles, a medium-range model with thermal sensors to track moving targets, and a long-range high-altitude platform that can exploit flight paths below the radar horizon to reach separated strategic infrastructure such as refinery towers. All serve a single logic. Instead of trying to punch through each expensive layer of defense, change the rules of the game, strike the logistics and supply chain, and force the enemy to make painful choices between protecting the front or protecting the rear. Finally, while much is said about tactics and engineering, it must be noted that the cheap swarm plus AI model is ambivalent. It can reduce casualties if used to precisely neutralize military targets and degrade attack capabilities, but when it spreads without legal norms and controls, it can also drive proliferation and new security risks. Therefore, technological innovation must go hand in hand with transparent norms, auditability, and accountability, a conversation NATO and the international community must put on the table now. But it is the number of missiles, the reload time, and the Pantsir S-1 operating procedures that form the strategic vulnerability these platforms exploited, and that is what we will dissect in the next section. In modern warfare, effectiveness is measured not only by rounds on target, but by a cost-benefit calculation minute by minute, reload by reload, supply line by supply line. The Saransk strike is a cold lesson. When the attacker understands the value of the defender's individual rounds, they can turn the expense of defense into a strategic weakness. Start with the decisive figures. A short-range air defense system like the Pantsir S-1 is described as having 12 ready-to-launch missiles per cycle, each missile potentially carrying a unit cost in the tens of thousands to hundreds of thousands of US dollars, according to the transcript. When the system fires 2 successive volleys, 24 missiles in total, to engage 24 decoy targets on the accounting sheet of war, this represents expensive resources consumed against low-value objects. The transcript estimates about 720,000 US dollars in material value for the decoys. The result is an economic attrition. The air defenses remain operational technically, but strategically they are paying the price. When a system runs low on missiles or is forced into a reload cycle, a time window appears, a temporal gap the attacker can exploit to insert real high-value targets. In the Saransk example, the mine storage was struck during that gap. The consequences were not only immediate damage, the transcript cites about 100 million US dollars, but also enduring effects. Reduced mine supply at the front, forcing the adversary to reallocate air defenses. The transcript mentions withdrawing roughly 50 Pantsir systems from the front line and opening new tactical seams. Reversing the economic equation is not, however, an invincible play. The opponent can adapt, increase missile stocks, deploy more firing positions, optimize reload logistics, or develop countermeasures, ranging from faster reloading procedures to more distributed defense layers. Each adaptive measure requires cost, time, and supply chain effort, and that is the intersection. Whoever can bear the long-term cost of adaptation will win the endurance race. Strategic conclusion. Saransk demonstrates that software, data, and cost models can redefine air superiority, but it also poses a stark question for defenders. Will they pay to preserve an expensive curtain of defenses, or will they restructure to meet the low-cost warfare model? And as the adversary begins to adapt, what are the technological and strategic limits of the swarm model, and what risks lie ahead? At the heart of the swarm and vision approach lies a clear operational envelope. It performs best when the attacker controls the information environment beforehand and the targets are discrete, militarily valuable nodes, depots, production lines, and specialized infrastructure. This method is not a recipe for random sabotage or indiscriminate harassment. It becomes decisive when concentrated strikes can produce outsized, lasting effects on the enemy's material flow. In Saransk, the objective fit that profile. A munitions factory whose neutralization degrades frontline capabilities without the ambiguity that comes with attacks in dense civilian areas, and therefore aligns with a cost-effective targeting logic. Practical effectiveness is the product of multiple synchronized elements. High-quality intelligence, SIGINT, ISR, and human reporting supplies timing and target context. Robust software enables image-based navigation when satellite signals fail. Coordinated use of decoys forces air defense systems to expend expensive interceptors, and precise timing exploits reload cycles and reallocation windows. When those pieces align, attackers can inflict substantial damage for a comparatively low outlay, trigger cascading shortages across supply chains, and gain tactical space while presenting the defender with difficult resource trade-offs. Limitations are equally concrete. First, the approach is data-dependent and environmentally constrained. Image matching requires good baseline imagery and favorable visibility. Dense fog, heavy snow, heavily altered urban terrain, or deliberate environmental deception will degrade accuracy. Second, defenders can adapt dispersing stockpiles, varying logistic schedules, hardening signatures, adding sensor layers, or improving rapid reload procedures. Each countermeasure erodes the initial asymmetry. Third, the proliferation risk is real. As cheap swarm techniques and AI navigation become widespread, non-state actors and irresponsible regimes may adopt them, multiplying threats and complicating attribution and control. Strategically, the model forces an adversary into agonizing choices between protecting forward forces and securing rear areas, but it is not an infinite lever. Sustained success demands persistent intelligence, resilient logistics for drone production and deployment, and a tolerance for the political and legal consequences of using such systems. As the technology spreads and opponents adapt, the crucial dilemma becomes one of balance. How to harness the strategic advantages of cheap, data-driven swarm tactics while containing the security, legal, and ethical risks they unleash. When technology changes the nature of the game, the question is no longer can we do it, but how far should we go? At the edge of every technical advance lies an ethical boundary. Is our strength meant to deter or to destabilize? The cheap swarm tactics paired with image-based AI, as in the Saransk scenario, highlight a slew of responsibility, legal, and security issues that any state, alliance, or manufacturer must confront before turning it into a strategic tool. First is the principle of distinction and proportionality. Under international humanitarian law, a lawful military objective must be clearly distinguishable from civilian objects, and incidental civilian harm must be weighed against the anticipated military advantage. An attack on a weapons factory can be lawful, but only with convincing intelligence and mitigation measures to reduce civilian risk. Therefore, any AI-based system must have robust verification processes. Algorithms should not become the sole arbiters of whether to strike. Next is the human-in-the-loop principle and accountability transparency. No matter how accurate the algorithm, the final firing decision must be subject to human review, traceable, and auditable. Retaining audit logs, timestamps, ISR metadata, and decision-making procedures creates legal accountability essential if disputes or allegations of violations arise. Systems lacking post-action verification and transparency will erode the legitimacy of military action and increase the risk of serious errors such as false positives. Cybersecurity and proliferation risks are another clear danger. As software becomes the critical component, vulnerabilities across the software, supply chain, satellite imagery repositories, or command links can be exploited. The spread of cheap swarm plus AI technology into commercial markets or uncontrolled third parties will raise the likelihood of non-state actors' misuse, techno-terrorism, and uncontrollable regional instability. Export controls, software security standards, and international cooperation are therefore necessary to keep this technology from falling into the wrong hands. Strategically, actions like Saransk, while effective, carry escalation risks. Striking rear areas may prompt the defender to widen rules of engagement, respond with greater force, or draw in third parties, potentially expanding the conflict. Thus, operational innovation must be accompanied by diplomatic strategy, transparency with international partners, military-to-military channels to deconflict, and diplomatic pathways to reduce the risk of miscalculation. Alliances such as Nato have a dual role to support development of civil defense standards and technologies and to set ethical and legal frameworks for using swarm and AI in operations. Those standards should include target confirmation conditions, human-in-the-loop requirements, post-event audit and reporting, software security criteria, and mechanisms for intelligence sharing to prevent misunderstandings. At the same time, investment in civil defenses, sensor networks, resilient logistics, and counter-swarm capabilities should be encouraged so critical infrastructure can be protected without diverting all military resources to rear area defense. Finally, there is the human element. Political leaders, military commanders, and citizens must recognize that tactical innovation does not remove political and ethical responsibility. Powerful technologies must be embedded in clear legal frameworks, civilian oversight, and diplomatic commitments about their use, because power exists not merely to win battles, but to preserve the international order we intend to keep. So what is the larger implication beyond the battlefield, and what political and legal lessons must be drawn now before this technology becomes widespread? When the sun rose over the Moldovan sky on the morning of the 10th of November 2025, smoke still rose from the Saransk industrial zone. But those plumes did more than mark a successful strike, they signified a turning point in the history of modern warfare. That night, 48 cheap drones achieved what generations of generals once believed impossible. They defeated an air defense system worth millions of US dollars with software and data. A strike costing under $1.5 million US dollars inflicted hundreds of millions in damage, shattered logistics, supply chains, and forced the adversary to pull dozens of Pantsir systems back from the front to protect the rear. Beneath that cold economic arithmetic lay a deeper lesson about mindset, responsibility, and the limits of technological power. Modern war has entered a new era in which software has begun to replace iron and steel in shaping outcomes. The victor will not always be the strongest party, but the fastest to adapt. Battlefield drones such as the AQ-400 do not symbolize wanton destruction so much as a shift from physical force to intellectual power, from mass devastation to precise, deliberate, and controlled strikes. The world is witnessing a new form of smart deterrence, where victory no longer comes from inflicting the greatest losses, but from forcing the opponent into the most costly choices. Yet every innovation brings ethical responsibility. If low-cost warfare can compel a wealthy adversary to pay a high price, it can also entice a weaker actor to take reckless action with technology they do not fully understand. If image-based AI navigation helps avoid striking civilians, the uncontrolled spread of the same technology can open the door to non-state actors, actors who are not bound by law or ethics. Therefore, while the world lauds technical achievements, it must remember that law and ethics must advance in step with technology. The impact of the Saransk strike goes beyond numbers. It changes how strategists worldwide think. Air superiority is no longer synonymous with having more aircraft or stronger radar, but with the ability to maintain control of the skies while optimizing cost, reducing risk, and protecting human life. From now on, small defense startups with excellent software, sufficient data, and networked integration can become major players. That is the future NATO, Europe, and the United States must prepare for, a world where technological innovation outpaces policy formation. That is also why the story of the 10th of November 2025 should not be viewed as a mere military victory, but as a strategic warning. Power, if not checked by wisdom and responsibility, can quickly exceed its original intent. Peace does not spring automatically from technology. It depends on how people choose to use that technology. For this reason, every country, large or small, should see the value of smart deterrence. Use power to prevent chaos, not to amplify it. In a world where a cheap drone can shape global politics, power no longer lives in the blast but in the decision not to fire. That is the essence of modern deterrence, the ability to control, to restrain, and to substitute intelligence for instinctive reaction. In the end, technology can change the rules of the game, but only humans can decide whether the game ends in peace or destruction. If you believe the future of warfare lies not in violence but in understanding and cooperation, join us as we dive deeper in the next section, where we analyze how technologies such as AI-enabled battlefield control and distributed air defense can be used not only to attack but to defend, deter, and preserve the global order. Power is not to dominate, it is to prevent disorder. That is the final message of the 10th of November 2025, when the Saransk sky rewrote the rules and the world began to redefine what peace means in the technological age.